Welcome to our lesson on work, and the dot product. So we're going to see that this concept of work is really an application of the dot product. So this concept of work really comes from physics. So I'll just kind of explain what work means from a physics perspective. Let's say you have an object. In my artistic skills, I chose to draw a rectangle, so it's some object, and we want to move this object. So this object's attached to a rope or whatever, and we're pulling on it. So we're going to apply a force in the direction of the rope, and then the object is hopefully going to move along the ground. Okay, so we're applying a force in this direction, and the object is moving in this direction. Then the work done by this force on this object is going to be defined as work done by the force, by F, the force being applied to the object is equal to how far we move the object, so the distance traveled, the distance traveled by the object times the magnitude of the force, but only in the magnitude of the component of the force in the direction the object moves. Well, I can't spell. Controls. Magnitude. Still can't spell. Of, what was I even saying now? The magnitude of the force of the component of force in direction object moves. Okay, so I don't know, that might be a little bit wordy. So let's just kind of draw one of those free body diagrams, or sort of like that. Okay, so here's F. That's F. Well, we know that F is made up of two components, a horizontal component and a vertical component, right? So sometimes we call that Fy because it's in, if the X was horizontal, Y is vertical, then that's in the Y component, and that's F, or Fx. So if the object is moving in this direction, then this is the component in the direction the object's moving. So work, or W, is going to be equal to the magnitude of Fx times, and then the distance the object traveled. So let's let S be the vector, which gives us the distance. So we'll say the magnitude of S. Okay. So magnitude of Fx times magnitude of S. S is in that direction. Okay. Probably should have had vectors on those F's, even the components. Okay, so there we go. We got a formula. Although this isn't F, right? It would actually, in a question, we're probably going to give it the force, not the component. So let's try to relate this to F. Well, we know that if this is the angle theta, then Fx, the magnitude, is equal to cos theta times F, vectors, So just putting this into there and rearranging, that'd be equal to the magnitude of F times the magnitude of S times the cosine of theta, which you might remember from dot product lesson. That's just the dot product. So F dot S. So the work done by F on S, or on the object, is equal to F dot S, where F is the force and S is the distance traveled by the object. Oh, one thing we should probably, before we do an example, we'll just talk about the units. So work is a new sort of measurement, right? So we're going to need units for work. So remember that work is equal to the magnitude of the force times the distance. So we know that distance we measure in, let's say, meters, and force we measure in newtons. So work, the units, will be newtons times meters, so Newton meters, which sometimes we'll call a joule, or we'll write it as the letter J. So that's a joule. Okay, so here's a very straightforward example. There's an object being pulled across the floor as shown in the diagram, so similar to the way we explained it above. It must be attached to a rope or something, and we're pulling it at an angle of 45 degrees to the ground, and the object is traveling right across the floor. With the force here is equal to the magnitude of the force is equal to 10 newtons, and we want to move the object 2 meters, so that would be the magnitude of S, and we want to know how much work's done. So work is equal to F dot S, which is equal to the magnitude of F times the magnitude of S times the cosine of the angle between them. So magnitude of F is 10 newtons. Magnitude of S is 2 meters times the cosine of the angle between them is 45 degrees. So that's going to be 20 Newton meters times the cosine of 45, which is equal to 0.7, let's go to 3 decimals, 0.7. So we're going to get, that's 14.14 Newton meters, which is 14.14 joules. Okay, so that's how much work is being done by this force on this object.